Hi! In this third video, we will continue with a case study in which we are estimating an unknown force applied to a second-order system with uncertain damping. In the previous video, we addressed how to build the weighted generalized plant and carry out h2, h infinity, both over the nominal plant, and mu synthesis over the uncertain plant. Performance results were obtained just numerically, and in this video we will interpret those results in both diagrams in frequency domain, and we will also reduce the order of the mu synthesis result. If we review previous videos, we had this uncertain system whose transfer function was this one nominally, but with the coefficient multiplying s being an interval. We had some process noise that generated a band-limited disturbance capital F, and we crafted a generalized plant in which we added measurement noise multiplied by some constant weights and fed the known input u and the measured position to an observer to be designed with h2, h infinity or musyn, so that it would output an estimated force, and we had some frequency-dependent goals on the estimation error, the difference between the actual force and the estimated one. H2 synthesis had only constant input weights, and we got some optimal H2 controller, minimum variance of the estimation error. But H infinity and mu synthesis added some output weights because we asserted that our goal was achieving a worst case amplitude of the estimation error below this thick red line, the minimum of 2 templates. So we built a generalized plant, and H infinity synthesis with the nominal plant gave nominal performance gamma lower than 1, but we did not have robust performance because the worst case gain was 2.33. So for some value of the uncertainty and some frequency, the error was above the required limits given by the output weights. On the contrary, mu synthesis did achieve robust performance because the worst case gain, considering modeling errors, was below 1. But mu synthesis spitted an observer of order 23, and that's deemed too large an order, so we will start by reducing the order to something more manageable with an acceptable performance loss in terms of worst case gain. So if we look for balanced reduction, the Hankel singular values of this observer are sort of 7, 6, 2. We have a couple of 0.1, but okay, this 0.02, the eighth one, is kind of very small, so we may aim for a balanced reduction of 7. And, well, if we look at the eigenvalues, we see that there is a pole in minus 341 that, we may also wish to eliminate if we don't lose performance. We will eliminate that pole with a frexep MATLAB command, got a frequency of 200, so we will keep the slow components, all poles with natural frequency below 200, and only the DC gain of the fast components. Then we get these 6 poles that are, the same as above, but look at the 10 squared factoring here. So we will check whether we have lost performance or not with this 6-order observer, and if we close the loop with an LFT interconnection of the weighted generalized plant and this reduced order observer, we get a worst case gain of 0.9965, so we're kind of lucky, in the sense that I would have expected a performance loss due to model order reduction, but it seems that performance loss is within the numerical tolerances of the worst case gain command, so it's kind of giving the same performance value as with the 23rd order initial observer. It's a matter of luck and numerical precision. Anyway, if I reduced this to order 6 and I delete also the pole at minus 374, then now the worst case gain is 10. So now we indeed have eliminated from the dynamic something which actually was very important. So we'll be back to order 7 plus elimination of fast pole with cut-off frequency 200, yielding a 6th order observer. That's the one, OO mu red, that we are going to compare with the H infinity, which was order 5, and with the H2 that was order 3. So we will carry out a performance analysis comparing the 3 design options in frequency domain, which is what the frequency templates are pursuing in H infinity and mu synthesis. H2 somehow minimizes the integral of the frequency domain, the variance and the weights were different, so kind of it plays in another league, but it's good to see it just to compare what the different optimization criteria do. The last video of this case study will discuss performance in time domain. So we will first look at the both magnitude diagram of the actual observer. It has an input U and an input Y measured, so you can see somehow the amplification of high frequency noise. The lowest one is the yellow thing, the H2 minimum variance stuff, and H infinity and even more mu synthesis have more high frequency amplification, so that it will almost certainly result in a larger variance in time domain simulations, but we'll see that in another moment. Regarding the frequency response from U, well, it's kind of difficult to interpret in the sense that what we are aiming for is for some frequency behavior of the estimation error and not of the actual estimation. So you can just forget about this plot. Maybe I even shouldn't have shown it. And let's go with the important one, which is the LFT interconnection of the generalized plant of the H2, H infinity and mu synthesis reduced, in which the inputs, process noise and measurement noise are multiplied by the suitable weights, so that amplitude 1 means the suitable amplitude in actual physical units, as in the problem statement. So we do these 3 both mag plots, and first we will plot the nominal value. So if we have a look, the first thing we can see is that the H2 and H infinity designs perfectly cancel the effect of the known input. Minus 200 decibels is just plain zero. Indeed, we know that nominally observers do cancel out the effect of known inputs in the estimation error. However, that cancellation will not be perfect once we are confronted with modeling error. So as mu synthesis knows it, it's the red line in here, then it will aim to minimize the worst case error without paying too much attention to the nominal performance. So there is kind of a crosstalk between the effect of the known and unknown inputs, but that's unavoidable with modeling errors. So the yellow and blue lines are an idealistic nominal case. So I will redraw, concentrating on the upper part of the figure. And then now we see, well, the important one is the middle one maybe, is how force estimation error compares with the actual force frequency content. The open loop yellow line is the actual force worst case amplitude. The template for H infinity designs is highlighted in red here. And the yellow line is the minimum variance h2 observation error, which, well, as the templates were not used in the way they generally planned, it just pursues a different objective, so no surprise that it doesn't match the templates. Anyway, h2 minimizes the integral, not the frequency to frequency template, so it's kind of a reference minimum variance design for later comparisons. But if we concentrate on the h-infinity in blue or mu synthesis in red, then we see that, of course, both achieve nominal performance. And in fact, the performance limit at this frequency and maybe at this one is better for the blue h-infinity result because it concentrates on optimizing the nominal model. The effect on observation error of measurement noise, if we look at the plot at the right hand side, is the lowest in the h2 design, it's a bit higher in the h-infinity design, and the highest one is the mu synthesis observer, because somehow uncertainty forces the observer to have a higher gain feedback, let's say. Well, anyway, this is nominal performance, and this is not what mu synthesis pursues. We will now plot the same both diagram, but throwing the dice and generating a handful of random plants, which is the performance under modeling error. In this case, we see on the left that the perfect cancellation of the effect of the known input is no longer possible, so h2 yellow and h-infinity have a worst case effect which is worse than that of the red mu synthesis option. And indeed, we also can look at the effect of the modeling error in the estimation error of changes in actual disturbance force. We see that, of course, h2 plays in another league, and h-infinity, which had a very good nominal performance, now it goes over the template in here and in here, but mu synthesis never touches the limit template. Well, it almost does in here, so that's why gamma was 1. So as expected, the best worst case performance was the mu synthesis observer, even if it did not have the best nominal performance, of course. As measurement noise does not go through any uncertainty, then this bow diagram is identical to the nominal case. So we'll end up the video here. The meaning of all this stuff in time domain will be left for a forthcoming video. In here we will just conclude saying that these both diagrams confirm the numerical worst case gain results on the weighted generalized blend, and we see that the template bound is not met by the h-infinity when we have modeling errors, but it is indeed met by the mu synthesis option. So we end the video here. Thanks for watching.